Thanks for the introduction. Okay, hi, I'm Seunghun Lee from University of Maryland. First, I would like to thank all the organizer, Jennifer and Lucas and Yang, for organizing such a nice workshop. I'm enjoying that, and everyone does, probably. So, yeah, actually, my talk is a little bit simple physics, but it's really difficult to experimentally observe. So I'm going to talk about the observation of perfect Andreev reflection in the topological superconducting states as a manifestation of the Klein paradox. So I guess everyone tired now, so let's start with really simple things. So everyone has experience to solve this problem, so-called quantum potential step problem. So by solving the boundary condition with wave function from Schrödinger equation, we can see how particles can behaves and when the particle meets such kind of potential step. So we can calculate the reflection coefficient and transmission coefficient. And we can do the same thing for the different potential barrier, like the delta function barrier or the rectangular potential barrier. So the transmission coefficient get complicated a bit, but we can still get it. But afterward, the Dirac tried to combine Schrödinger equation and the relativistic theory. So basically, he wants to use the relativistic energy and then to solve this equation. And then he introduced the matrices, so-called gamma and Dirac matrices, which consisting of Pauli matrices. And then he got the relativistic Schrödinger equation, so-called Dirac equation. And after that, Oscar Klein did the same thing, what we just solved with Schrödinger equation. So he tried to solve the quantum step problem with Dirac equation. And then he realized that reflection coefficient is always zero, regardless of the height of a potential step, which is known as Klein paradox. So basically, in the relativistic quantum realm, the reflection coefficient should be always zero. So now we have to think about how to observe that. So maybe simply, we can think of the accelerating particle at the speed of light. But we have the group platform, as everyone knows. So some material described by Dirac equation, so-called Dirac material, like graphene or topological insulator. Actually, I took the concept of this figure from the Yang's presentation when he gave a talk in the University of Maryland. Okay, I guess everyone familiar with topological insulator, but let me just quickly go over something important. Simply, the band structure of topological insulator looks like this. So basically, Fermi level is resides in the band gap, but it goes across the boundary states. So naively, we can say the bulk state is described by Schrödinger equation, and boundary states is described by Dirac equation. And as a result of the spinor in the wave function from the Dirac equation, it has spin momentum locking. So now we can think the topological insulator could be a good platform to observe such relativistic quantum phenomena. So now the question is then, any topological insulator can be used for that. So here's some representative result of the well-known topological insulator. But all the result indicates that the band structure of most of TI looks like this. So Fermi level across bulk states as well as the boundary states. So every time if we measure transport properties from such kind of topological insulator, we always have kind of mixture of particles described by Dirac equation and Schrödinger equation. So samarium hexaboride ray has lots of attention as the topological insulator. So basically, samarium hexaboride is a condo insulator. At the high temperature, it behaves like metal. But at the low temperature, the hybridization of samarium 5D and samarium 4F is getting stronger. It opens the gap. So as a result of strong spin-off coupling and then the inversion, it becomes a topological insulator. So there is several reports suggesting that the samarium hexaboride is topological insulator from the transport measurement to the STM measurement. So simply the Dirac-like dispersion relation, the dispersion structure has been proved by RPES and STM measurement. Actually, I just realized that this result actually posted just on the archive, but isn't published in Nature Physics. It's gonna be published in Nature Physics. And the spin-dependent structure has been demonstrated by the spin RPES and spin-dependent thread. So if you are interested in such kind of result, I just recommend to look up these papers. Okay, so in our group, we have studied some hexagonal thin films. So first, we have studied the stoichiometry effect on the electrical properties of samarium hexabolide by combinatorial approach. And then we also have studied the superconducting proximity effect on from the bilayer structure consisting of superconducting niobium and samarium hexabolide. And we suggest that the superconducting proximity effect in this system is exclusively coupled with surface state of samarium hexabolide. And then we succeeded to grow the high quality samarium hexabolide thin film. So in general, if you look at the other literature, most of the samarium hexabolide thin film has polyplex structure. But we succeeded to grow epitaxial samarium hexabolide thin film. If you look at the TM image, not TM image, the electron diffraction pattern of silicon and samarium hexabolide thin film at the interface, we can see the epitaxial relation between samarium hexabolide and substrate. Okay, so now we have a material to observe relativistic quantum phenomena. Samarium hexabolide is going to be a good platform to observe that. So now we have to think about the measurement. What kind of measurement is suitable to observe that? So first of all, some transport measurement should be described by such kind of information of particle incidence and reflection and transmittance. And then basically the Klein tunneling is nullifying the barrier, basically the perfect transmission even under the presence of the barrier. So such measurement should be sensitive presence of the barrier, and such barrier should be modeled, physically modeled and describable. So we choose point contact Andreev reflection process which satisfy these conditions. So basically point contact Andreev reflection is the one of point contact spectroscopy measurement, but it's based on the Andreev reflection process with superconductor. So we can make a point contact using soft point contact method or the DND techniques. And we just measure the differential conductance as a function of bias voltage. So let's see what Andreev reflection process is. So basically Andreev reflection process is a whole reflection at the interface made with a non-superconductor and superconductor. So if we make such kind of interface, and if we flow the electron from the normal metal, the electron itself cannot penetrate into the superconductor itself when the energy of the electron is less than superconducting. Yeah, it should create a Cooper pair. So to conserve the charge and spin, the whole should be reflected at the interface. So as a result of whole reflection, if we measure the conductance spectrum, we're supposed to see the conductance doubling when the energy of the electron is less than superconducting again. So that's extremely ideal condition. In general, it is difficult to observe such kind of conductance doubling because there is always barrier at the interface. It creates the electron reflections at the interface. So such kind of barrier could be due to some contamination, oxidation, and the Fermi velocity mismatch. And such kind of interfacial barrier is modeled by delta function with the height which modeled by z value. So in this paper, so-called BTK theory, consider everything, including z value. So with the increasing z value, basically height of delta function, the conductances get reduced. Okay, so the point context Andreev reflection measurement could be a good platform to observe such relativistic quantum phenomena because it's described by quantum mechanical particle traveling process, and they're also really sensitive to the barrier. So now we have material and measurement. But we need superconductor to use point contact Andreev reflection process. So we come with some idea to make the samarium hexabolide superconducting. So simply just make samarium hexabolide on the yttrium hexabolide as superconductor. We can make samarium hexabolide superconductor. So here is several necessary condition of superconductor. So basically higher TC is better because it makes much easier to access such kind of measurement. And then the most important thing is growth condition regarding in terms of growth condition. Because to grow the high quality samarium hexabolide thin film, we need to use very high temperature, above 800 degrees Celsius. So in such case, we can use just the metallic superconductor. Definitely, if we grow samarium hexabolide around 800 degrees Celsius, it ruins the surface interface. So we cannot get the ideal superconducting proximity effect. And we found that the yttrium hexabolide is superconductor. So there is a lot of benefit by taking the yttrium hexabolide. basically the samarium hexaboride, yttrium hexaboride have same crystal structure and almost same relative parameter. So we can expect that we can use the same growth condition to grow yttrium hexaboride and samarium hexaboride because both are hexaboride systems. So we can do the in situ thin film growth bilayer fabrication for the yttrium hexaboride and samarium hexaboride in such case. So in preliminary, we studied the stoichiometry effect on the superconductivity of yttrium hexaboride. Because there is several reports on the superconductivity of yttrium hexaboride, but the TC of yttrium hexaboride is completely inconsistent from 2 Kelvin to 8 Kelvin. So we studied stoichiometry effect by combinatorial approach, and we found that it's slightly boron deficient yttrium hexaboride has maximum TC. Then so we fabricated samarium hexaboride, yttrium hexaboride system and measured the point contact spectrum. And then we observed that for the specific thickness of samarium hexaboride, we observe a perfect conductance doubling, so-called perfect Andreev reflection. So this result can be interpreted by 2 different scenarios. One is simply z equals 0, or something related to the topological protected states. So at the beginning, we look up the literature on the peak measurement on the variety of superconductor. So here we plot the conductance enhancement at the 0 bias versus the z value. So if you look at all the points, every points were captured by standard BTK theory, which I showed you before. And there is only 2 reports showing the perfect conductance doubling, which is a special case for the niobium and copper junction when z equals 0. So I will explain that why this z equals 0 scenario is not applicable for the samarium hexaboride and yttrium hexaboride system. Okay, so to interpret this result, we have done very systematic study of thickness dependency or yttrium substitution effect and magnetic field dependency. Let's look at one by one. Okay, first the yttrium substitution effect. So if we put the yttrium in the samarium hexaboride layer, we can see the conductance doubling. So basically, the purpose of this experiment is tuning the Fermi level as a mimicking of other topological insulator system. So basically, this work is initiated by the fact that no one has observed the perfect conductance doubling for the other topological insulator and superconductor system. So here's the band structure we expect from samarium hexaboride. But if you think the basic nature of samarium hexaboride and yttrium hexaboride, samarium hexaboride is an insulator, and yttrium hexaboride is metallic. Basically, it's due to the different balance state of samarium and yttrium in the hexaboride system. So we can expect yttrium can be the donor in the samarium hexaboride system. So which can increase the carrier concentration, and we can make the conducting bulk states for that. So we put the yttrium, and with the increasing yttrium concentration in the samarium hexaboride, the resistances get decreased and it's become completely metallic. And then we fabricate yttrium substituted samarium hexaboride on yttrium hexaboride now to make the superconducting states. Now if we measure point contact spectrum on the yttrium substituted samarium hexaboride, now because bulk is conducting, so the proximity induced superconductivity in the yttrium substituted samarium hexaboride now is kind of mixture of topologically trivial and topologically non-trivial superconductor. So this is the reason why we can see the perfect Andreev reflection. So now let's look at thickness dependency. So we can see the significant change depending on the thickness of samarium hexaboride. So let's look at one by comparison. Okay, first, if the thickness of samarium hexaboride gets thinner, we can see the perfect Andreev reflection. So this result can be interpreted by the hybridization of the top and bottom surface states. So here is the band structure we expect, but if the thicknesses get thinner, now the top and bottom surface state is going to be hybridized, and it opens the gap, and it weakens topological protection around the Fermi level. So this is the reason why we can see the perfect Andreev reflection for the thinner samarium hexaboride layer. And if we make samarium hexaboride thicker, we can see any feature related to the superconductivity, see? And this result is consistent with general point context spectroscopy measurement on the yttrium samarium hexagonal. So this information only delivers the information of the band structure of samarium hexagonal. So we can interpret this result. If the thickness of samarium hexagonal get thicker, now the inside bulk states also get thicker. So the inside bulk state behaves like a barrier for propagating superconducting Cooper pair from yttrium hexagonal to the top surface of samarium hexagonal. So that's why we can't see any proximity-induced superconductivity on the top surface of samarium hexagonal. Now let's look at most important result we got. So if we measure the point context spectroscopy, point context spectrum of yttrium hexagonal itself, it shows conductance dip, which is completely opposite to the samarium hexagonal yttrium hexagonal bilayer system. So actually, this can be understood really easily with the standard BTK theory. As I mentioned before, the Z value can be estimated by the Fermi velocity dispatch, according to this equation. So if we take the Fermi velocity of yttrium hexagonal, the Z value is going to be 1.4. So if we simulate the conductance curve with the BTK theory using this Z value, it shows conductance dip, which is consistent with what we got from experimental result. But actually, this standard BTK theory is not applicable for the samarium hexagonal yttrium hexagonal if we consider the Fermi velocity of samarium hexagonal. The Fermi velocity of samarium hexagonal is not clear yet, but it's ranged from 10 to the 4 to 10 to the 5. So if we take 10 to the 4, Z value should be similar with the yttrium hexagonal case. But if we take 10 to the 4, Z value is even much higher than the Z value for the yttrium hexagonal and the normal metal. So this standard BTK theory is not applicable to understand this perfect Andreev reflection we observed in samarium hexagonal, yttrium hexagonal bilayer. So our theoretical colleague to modify this standard BTK theory with Dirac equation. So we call it Dirac BTK theory. So according to this theory, no matter what Z is, we always got the conductance doubling. So let's see what the Dirac BTK theory tells us. So basically, if you measure the point context spectrum of each single yttrium hexagonal, it shows conductance dip. So because of electron deflection at the interface. But if we put the samarium hexagonal on the top, we need to consider the two different effects. From yttrium hexagonal to samarium hexagonal, there is superconducting proximity effect. And there is another proximity effect from the samarium hexagonal to the normal metal tip, which is the topological proximity effect. So in such case, now this system is completely changed. This superconducting side is going to be topological superconductor. And this normal metal side is going to be topological metal. Basically, this metal side inherent spin moment locking properties. So in such case, electron deflection is not allowed anymore. So this picture can be understood by spin moment locking. So because now the Dirac equation, this system is governed by Dirac equation. So basically, we can see that this spin momentum locking actually now can apply for the both sides. So samarium hexagonal has a helical superconducting pair, and the platinum iridium side has spin momentum locking from the samarium hexagonal. So in such case, electron reflection, which has the same spin direction to the incident electron, is not allowed. So we also have the field dependence study. So for that, actually, we fabricate thin film junction, which all the junction is made by the thin films, which is kind of soft contact method. So if you look at the field dependence data, with increasing the strength of field, the conductance enhancement get decreased. That's reasonable because the magnetic field kills the superconductivity. But actually, most important result can be found in the directional dependency. So if you look at if you compare the magnetic field along outer plane and in plane, the conductance enhancement decreases much quicker when we apply magnetic field along outer plane. But if you look at the gap size estimated from the width of the peak, it's almost same. So that means this difference is not only due to the superconductivity itself. So it can be understood by the spin momentum locking and band changing the band structure by applying magnetic field. So if we apply magnetic field along in plane, the Dirac point is going to be shifted, but spin momentum locking is still preserved. However, if we apply magnetic field along outer plane, it opens the gap and it weakens the spin momentum locking around the Fermi level. So this can be, actually this picture also consistent with what we observed from the other experiments. And this basically if you look at the previous slide, I'm sorry. Okay, basically this picture tells us there is no electron reflection, there's only Hall reflection is allowed. So this Hall reflection indicated by perfect Andreev reflection is indeed a manifestation of the Klein paradox. Okay, now I'm going to close my talk with brief summary and perspective. Actually, we observed the relativistic corner phenomena by simple method, point context spectroscopy measurement for this system. And this result also indicate that samarium hexaboride is topological insulator. And the proximity induced superconductivity in the samarium hexaboride is indeed topological superconductivity. So everyone knows that the topological surface state of topological insulator can be used for spin-turning device. But actually, for the samarium hexaboride, we can completely exclude the bulk contribution, so we can get the highly efficient spin-turning devices. Of course, it's only available at a low temperature, the samarium hexaboride. And also, the topological superconductivity is related to the minor fermion physics, so it can be used for quantum mathematics. But we want to suggest that basically we observe this effect is nullifying the barrier effect in the superconducting junction. So such kind of superconducting junction array can be used for highly sensitive detector and the antenna application. But every time there is some problem, so-called decoherence problem, because all the superconducting junction is not identical. But based on our result, superconducting junction with topological insulator can nullify the effect of barrier, which liberating the decoherence problem in such kind of superconducting array application. Okay, so I would like to thank everyone for the support of this work. And we couldn't do this work with numerous support from the grant. And this is the end of my talk. Thank you for your attention.